Dear students, welcome and thank you for tuning in to this video with me, Dr. Loay Al-Zube. We are still talking about the kinematics of a particle moving on a curved line as part of the statics and dynamics course, which is chapter 12 actually. So we have described in the previous videos how the motion of a particle traveling along a curved path would look like if we look at the position, velocity, and acceleration, and we have set the ground actually to move forward in a curvilinear analysis. Before doing that, we would like to a little bit add to our knowledge and to remind ourselves with can we relate kinematics quantities, which are position, velocity, and acceleration, to the rectangular components of the vectors, which are the x, y, and z coordinate systems. And it's going to be quick, but it's important to remind ourselves with it right now because we're going to use it extensively in our analysis later on. So a quick reminder, it's often convenient to describe any motion or the motion of a particle in terms of x, y, z. And this is easy, but it's not always the best way to go. But we would like to remind ourselves with the concepts, and we will move from this coordinate to other coordinates later on. So these rectangular components, they are relative to a fixed frame of reference. So you can say, if you recall from the beginning of the semester, we did something called the position vector. And so you refer the position of a particle to origin point. Let's say here it's 0, 0, 0. Let me change the color of my pen so that we can see it clearly. So yes, so if this is your point, reference point, and this is your location in the space, we can identify an R vector, which is called the position vector, and you will find these values x, y, and z, and then you have this is the reference 0, 0, 0, and you can identify your position vector by subtracting the latter from the former. So the position vector is x, y, and z. Remember, it's x final minus x initial, y final minus y initial, and z final minus z initial, and then this is where you get your position. Since our reference is 0, 0, 0, we just put the x, y, and z. They can be a function of time, because if you're changing your location, they will follow a formula. So I can put the x and y and z as x function of t, y function of t, and z function of t. And this is this is an addition to what we know before. And instead of looking at locations, which is numbers or coordinates, we are now looking at functions as function of time. And the magnitude, as always, going to be the square root of x squared plus y squared plus z squared at that specific point in time. And the direction of r is defined by the unit vector. And if you call the unit vector is the vector divided by its magnitude, right? So, and you get your unit vector, which is the direction of your vector. And we did this a lot. We did a lot of these in the previous lectures. Now, after the position, let's talk about velocity. Again, the velocity, it's a vector, and it's the time derivative of the position vector. So if you have r as a function of time, which means that x is a function of time, y is a function of time, and z is a function of time, you just derive all of them with respect to time, and you have your velocity vector. And ijk, they're constant in magnitude, direction. You can say that x dot vx is x. So the velocity, the x component of the velocity, is the derivative of the x component of the position. And that goes the same for y and z. And the magnitude, similar to the x, the position is the square root of the vx component square plus the vy component square plus the vz component square. The direction of v is always tangent to the path, and it's a vector, and we can find it by using the u of v, which is, as we said, it is going to be so if you want to find u for v, is going to be v divided by the magnitude of v, right? And that's your direction. But we want to keep that it is always tangential to the direction of the path. So this is about velocity. How about acceleration? Same thing. The acceleration is a vector. It's also the time derivative of the velocity and the second derivative of the position. So if you have r as have x, y, and z, and they're function of time, you can derive them the first derivative, that's the velocity, second derivative, that's your acceleration. The magnitude is similar, square root over the x component square plus the y component square plus the z component square, and the direction is usually not tangential to the path, but it is actually you can find it from the Hodo graph, and we talked about this in the previous video, how to identify the direction of the acceleration. I hope that this is helpful. It's just a quick review, and it's just reminding us that we need to, in order to go from position to velocity to acceleration, you need to do the derivative. The change here is that each one of those, the x, y, and z components, are functions of time, and we need to pay attention to that. In the following videos, I'm going to solve problems and show you how to use these concepts. So in summary, we were able to relate the kinematics variables with the rectangular coordinate system and see how we can get velocity and acceleration from position. You can also get position from velocities and acceleration using integration. Thank you for watching, and to the next video. Bye.